All right, we're live. Going to introduce, this talk is about PowerMAN. Did I say that right, Jesse and Brett?
Yes.
Yeah.
Welcome to the PowerMAN talk.
Right, which is, so it's Jesse and Brett, Dynamic Interface Power Management. As usual, we'll go with the video first, and then there'll be Jesse and Brett will show up at the end for Q&A. So I'm going to get this started now, and we'll hide.
Hi, everyone. Welcome. We'll be talking to you today about a proof of concept we'd like to call PowerMAN. So let's get started. As usual, a word from our sponsor, the typical disclaimers. There's a link here to Unsplash where all the images came from. So who am I? My name is Jesse Brandeburg. I'm a principal software engineer. Brett and I have both been working in the Ethernet products group for a while. I'm a longtime Intel employee working for Linux drivers, working in Linux drivers for 20 years now. My focus has always been making our products better, but I have a special fondness for both performance and for doing kernel improvements in both our drivers and the kernel proper.
Hey, I'm Brett Creeley, and I've worked at Intel for about three and a half years, and I just really enjoy fixing things and like Jesse said, making our product better, and that's it.
Today, we're going to talk to you about a little bit of the background about our presentation, the problem that we were trying to solve, and show you some results from our proof of concept. This problem that we have is both related to power management and to drop packets and throughput. So as far as drop packets go, sorry, I got ahead of myself slightly. Today's normal configuration has to do with for packet drops and throughput, and then there's also latency. In latency-sensitive environments, typical configurations usually cover something like 275 watts of power when the system's set to poll. So if you're really latency sensitive, you might set your system to polling, and then you would burn all this extra power just to get low latency. Other setups that are really common are throughput setups, where throughput is most important, but maybe the system owner would leave the system in low power states for idle to save power, but you also want to have high throughput, which works fine. Turbo works great with the low power configurations, but you have very high latency, and also it's quite unpredictable. These numbers were measured by turbostat on a 511 kernel. Where do packet drops come from? This is important to understand today for our NICs. It provides some background about one of the problems that we're trying to solve with this setup. Ethernet, particularly the Intel Ethernet cards, drop packets in two main places: the FIFO, which is the data storage on NIC. It's actually in a high-speed memory on our cards, or it's dropped from the driver's ring, receive rings, due to no available slots. So if the card successfully receives the packet off the wire, but it can't find a place to DMA it to in host memory because there's no room left in the ring it picked, then it could also drop the packet. There's also a third reason. Sometimes the stack will just drop the packet. So the card worked, the driver worked, everything was handled, and then we gave it to the stack and the packet got dropped somewhere. The causes of these three things is sometimes the DMA can be too slow or blocked, and so the FIFO storage is the only place where the packet can be kept, and it's quite small compared to wire speed. Sometimes the CPU is too slow to catch up, and sometimes there's just too much work to do on a particular core. So if the CPU is at 100% utilization, the packet may get behind in the queues and then be dropped. Sometimes for socket buffers, they're also too small, and particularly as you get into 100 gig and 200 gig networks, sometimes the socket buffer defaults on certain kernel versions were too small. Those constantly get adjusted, and they're also adjusted via memory size on the system, but sometimes it can help to increase those as well to prevent drops. Let's talk for a minute about power states on a system. so you know what we're saying when we say PC states or C states. In this case, package C states is what PC states means. It means that the uncore and the thing that controls the DMA is actually going to sleep if the system gets into a deeper sleep state than PC2. So typically you might see in turbostat something that mentions PC6, which is effectively the deepest sleep state that many of the Intel processors can get into today. And the bad news is, from a NIC's perspective, is that it prevents the DMAs to the host. So the only thing alive then is just the NIC and its controller, and it can't get data out into the host at all. The other piece of bad news is that the wake from PC6 to PC2, where DMAs can start again, is typically 40 microseconds, and it varies from processor to processor. And new processors are different than old processors, but a typical time is about 40 microseconds, and that's a lot of buffering at 100 gigabit. As I mentioned before, the drops from this DMA block is actually counted in ETH-tool in a stat usually called something about port drops. And if you're interested to see if your system is using a PC state, you can use turbostat. Let's talk about C states for a second. C states are core states. These are sleep states that are associated with the core freezing, but the package stays alive. So the DMAs aren't blocked, but the cores are idle, and so they go to sleep. Some desktop systems have a C10 state, which has got a crazy exit latency at 890 microseconds. C6 on a lot of modern servers is a lot faster than that. It also doesn't save as much power as a desktop or mobile processor might, but it has exit latencies in the hundreds of microseconds instead of near 1,000. The good thing is that the core is halted and asleep. The bad news is that it's not processing any work, and it has to be woken up to handle an interrupt or to process any NIC storage packets. Watch some presentations today on the first day of Netdev, and the scheduling guys from Google are doing the same kind of thing where they like to keep a core awake. That's part of our experiment as well. We'll talk about that in a little bit later. So DMAs can flow, and the driver needs to have an awake processor in order to process packets. In this case, if a packet is dropped because the ring was full, meaning that the CPU, for whatever reason, couldn't handle processing all the packets that were arriving on that queue, then this is counted in VSI drops. And you can see that in ETH-tool. You can also look at your system's available C states or core states with the CPU power idle info command or turbostat. This is really creating a problem for us in that we're storing data on our NIC to cover what's basically the ability to buffer across that DMA latency or the DMA wake up of the package C state. This slide shows us how much storage you would need to have to cover that 40 microsecond wake from PC6 to PC2. At 200 gigabit with 8 traffic classes, meaning the FIFO or the memory is divided into 8 pieces, you would theoretically need 8 megabytes to store 40 microseconds of incoming wire speed traffic. So a burst of traffic would need that much storage. So you can see the other sizes here as well. Really, using megabytes of memory on NIC or even hundreds of megabytes of memory in the host still doesn't solve the problem. What we really have here is that networking is creating this problem where we have these asynchronous events coming in, and they're unpredictable, and they arrive quickly or can arrive at any time. And so the system can be idling and saving power, but never knowing when it's going to wake up to get an Ethernet packet. This same 40 microsecond delay is now talking about C states, not PC states. So let's look quickly at this chart. In the case of, on the left side, you have the ring size of the ring sizes of the different rings. And in this case, we highlighted this line because it's 2048 buffers. That's the default for the ICE driver with a 100 gigabit card. Across the top here, we have the different packet sizes that this table is representing. What the red and the yellow are showing is the opportunity for drop packets to occur when you have a single queue taking in 100 gigabit Ethernet at line rate. Okay, so this is a somewhat unlikely thing, but it demonstrates that any core would have to wake up at least this fast. Otherwise, it's going to drop packets. So if there's 64 bytes of packets incoming in a burst, we're going to overrun our ring in 13 microseconds, which is a big problem because the core takes up to 40 microseconds to wake on average. That means sometimes it'll take longer. So this is just more drop packets. In this case, I was talking about hundreds of megabytes of memory. We allocated 477 megabytes of receive storage for 112 queues. That's a lot of memory to allocate. It's not ideal, but it still doesn't solve some of the problem. We still get drop packets. As network speeds increase, the kernel has to adapt. So what can we do? We wanted to design an experiment to see if we can save power and avoid suffering drops. So we wrote a bash script that runs the setup and the logic, and it uses the RSS table to shrink the number of active queues. And we can write to the RSS table at runtime by design in the hardware. So this allows us to keep one CPU awake using the power management APIs in the kernel and have it effectively distribute work out to other CPUs or increase the number of active CPUs if the traffic requires it. Otherwise, if the system is idle, we only have one core awake. And in this case, we are keeping that core at C1, which is a very low latency exiting sleep state. It's either 2 or 10 microseconds, and depending on whether it's C1E or C1. And this allows us to sleep, but wake quickly, and also only have one queue active until we need more.
Hey, this is Brett, and I will talk a little bit about the setup and the experiment. For the setup, we ran a back-to-back 100 gigabit Intel Ethernet adapter E810 with a Mellanox Connect X4, and we used the latest Intel driver from the SourceForge release, and the Mellanox driver was in kernel, and we used NetPerf 2.7. And then there's some details here on the right about the system under test that was running the script that we talked about. Next slide, please. For the proof of concept, we had two bash scripts. There was one for the initialization, and then there was one that ran the PowerMAN logic in a forever loop. Next slide, please. For the experiment setup, both systems were set up with local node queues only. And then for the baseline case, we had the system in C1 was the max sleep state, and then RSS was set to the equal number of queues. And then the interrupt rate was set to a constant 10 microseconds. For the PowerMAN setup, we had the system, all the cores in C6, except for the queues that were active. And then we had RSS directing to a single queue initially, and the interrupt rate was also set to a constant 10 microseconds. Next slide, please. So this shows the initialization sequence and then also the main execution loop. So the initialization sequence sets up the kind of system in a low power state with only one RSS queue enabled, and it's an associated CPU in C1, and then all other CPUs aligned with the queues are in C6 so they could sleep and save power. Then the main execution loop monitors receive packets per second, including drops. And then based on this, it'll choose to either increase the number of queues or decrease the number of queues. And so if we increase the number of queues, we will add one or more queues to the RSS table. And then we will also disable the higher sleep states and not allow the CPUs attached to those queues to go higher than C1. And then if we decrease the queues, we will reduce the number of entries in the RSS table. And then we will allow the CPU that was attached to that CPU or that queue or aligned with that queue to sleep and go up to C6. And then if we don't have any changes, we'll just loop back to the start and measure the packets per second again. And this just runs forever. Next slide, please. The test, we used netperf, and we used TCP-RR and TCP-Stream. Each test iterated from 1 to 128 threads, and then all of the results were averaged across all of these runs so we could get a little more consistent data. Next slide, please. In the coming slides, we'll show 4 charts, and there's a lot of data packed into those charts. So this slide kind of is a little legend or hint to what all of the graphs mean. So we'll talk a little bit about this. And if the retransmits are negative, it shows a benefit towards PowerMAN because we're having less retransmits. And if the CPU and power percentages are negative, this also shows a benefit towards PowerMAN. And then a positive transactions and throughput percentage show a benefit towards PowerMAN as well. And then the opposite, anything opposite of that would be a negative towards PowerMAN, and it's not helping. We also measured RAM watts, but we didn't show it in any of the graphs because the results just weren't significant. Next slide, please. So here you can see we have the receive case is what we call it, and the client is on the left, and then the system under test is on the right, and that goes for all of the slides. And then the system under test here is either running the baseline case or PowerMAN. And for these tests, we kind of found the difference and then averaged that, and this is what the graphs show. And in most of these tests, we saw the most benefit on the higher thread cases, so for 32, 64, and 128 threads. So we'll concentrate on those cases. For this one, we saw that the retransmits and the send CPU were much better with PowerMAN running. You can see in the 32 thread case a slight improvement for send CPU. And then on the second one, we really saw much less retransmits, over 3 million less retransmits in just the 30-second test. And in the 128 thread case where you see the dark blue again, we had about 6 million less retransmits. And then we also showed an improvement in transactions for all 3 of these cases in the green, about 10%, and then about 20% for both of the 64 and 128 thread cases. Next slide, please. And for this test, we called it our transmit test, where the client is sending 1 byte buffers and the system under test is sending back 64K byte buffers. And in this case, we'll talk about the 32, 64, and 128 thread case again. And you can see that our package watts difference for the system under test for the higher thread case was quite a bit less in the orange. So you can go from about 10% less in the 32 thread case, and then about 25% less in the 64 thread case, and about 30% less in the 128 thread case. Next slide, please. And here is our bidirectional case where we had send and receive 64 KB buffers. And again, you can see the most benefits in the higher thread cases. So for the 64 thread case here, we'll talk about our retransmits again are about 2.5 million less. And this, we also save power here and save CPU use. And then the same goes for the 128 thread case, where we had about almost 5 million retransmits less, and then we saved even more power, and the CPU usage was even less. Next slide, please. And here is the stream receive test where we were sending 16K byte buffers, and then the system under test was sending 1 byte buffers back. And in this case, again, you'll see the higher thread cases, the continuing theme are much better. Specifically the 64 and 128 thread cases, where you can see in the dark blue, the retransmits again were about 3 million less for 64 threads, and then again about 6 million less for 128 threads. And this corresponded to less power usage in the orange for both of those cases, and then also an increased throughput for both of these by about 20%. Next slide, please. And here are experiment conclusions. And we can safely say that PowerMAN prevented retransmits due to drops, and this helped us reduce the power usage, especially in the higher thread cases. And then one of the biggest negatives that we had here was that PowerMAN didn't think about transmit at all, and so there was no logic in the bash script that paid any attention to transmit throughput or transmit packets, so that our transmit specific tests didn't show great results. And then we didn't have huge benefits in the lower thread count tests. And I think one of the biggest things here was that we saw efficiency increase by consolidating the workload into fewer queues, which is where the RSS table came into effect. Next slide, please. Here are some general conclusions. And our key takeaway here is that reducing the retransmits and drops was able to reduce the power consumption. And then moving forward, we would like to test with the baseline in C0 to compare to PowerMAN, because you could really see a huge power savings in that case. And C0 can often be used for latency sensitive tests. And this would show an even bigger benefit towards the PowerMAN script or whatever we use going forward. And then we'd also like to incorporate transmit performance into the logic. And then we want to expand the testing tools to use something like, XDP, AFXDP, or other packet generators, and possibly forwarding workloads. Next slide, please.
What are our next steps? We could do a couple of different things. We could take the Python approach and do a script in user space to try and manage this instead in Python, and basically turning it into a daemon. The other option is to do something in kernel as the scheduler changes. And we might be able to use some of the presentations talked about in this conference, some of their cool new innovations about doing user space scheduling to rapid prototype some scheduler changes. However, we think there's some missing pieces that the scheduler doesn't have access to today that we need to implement in the kernel. The scheduler needs to probably become aware of how many cycles are spent in the interrupt handlers for the devices, and it needs to know a little bit more about which queues are associated with which netdev and then where they're routed to in terms of their interrupt. All three things need to be tied together so the scheduler knows about them. It also needs to have knowledge about queue overruns or drops to get feedback about whether the changes that the scheduler made are good or bad. And it's possible it could also know about dimlib or interrupt moderation changes that were occurring. Basically, the scheduler getting involved in setting these interrupt moderation rates because it knows what it's going to be asking the NIC to do next. We figured that this new scheduling algorithm would integrate all these things and choose to enable when to enable more RSS queues and balance the workload that way. So our final thoughts. The default configuration of queues today is suboptimal. Each vendor does it differently. Each NIC, even within vendors, does it differently. Telling users to pull their machine in C0 and burn hundreds of watts of power just to avoid a few drop packets or avoid latency or get the best latency is really unacceptable. There should be some middle ground here where we can get good power utilization and not drop packets or have latency unpredictability. The PowerMAN proof of concept, we believe, yielded obvious power savings in high thread count tests. We think the proof of concept showed what we wanted it to. It worked well, particularly for receive workloads. And we believe PowerMAN should become part of the scheduler in the future, and we're going to be working towards doing something like that. Any parting comments, Brett?
I hope that we can spend some more time working on this and make more progress and move it from a simple bash script. And we're excited to work on it. And thank you, everyone.
Yeah, thanks for coming today, everyone, and come join us in the next session if you've got it, and bring your questions or discussion, and we'll be glad to chat with you. Thanks for coming today.
All right. Okay, so I think I'm just going to post the questions here, guys.
Yeah, let's get started answering the questions. I've been looking over them. I think we're ready.
All right.
No, there's all sorts of PowerMAN jokes. It's awesome. Jamal, were you going to post the question? Okay, there we go. So the number of threads used for the power measurements, all we did was tell CPU power to just set the system into a particular power state. So it set system-wide, all CPUs, into no power management. And so the system was completely idle, but burning away with, at 275 watts. And this is an older system. Newer systems have different numbers, some worse, some better. So I think that hopefully answers that question, unless you want to add something else. I can also answer his next question.
So I think that we were having them in C1 as well, right? So they weren't quite burning 275 watts.
Yeah, he asked that question when I showed the 275 watt idle slide.
Oh, okay.
So yeah, that was early on. Yeah, and basically system was idle, but stuck in C0. So it just sits there idle and burning lots of power.
Right.
Okay, next question is from Srijit again.
Yep. Core wake-up latency is not accounting actual IRQ handling latency, right? So is this the DPTK style RX? No, it's not. We answering the questions in reverse order. The core wake-up latency that I was talking about is just the amount of time that the processor takes to go from not able to do anything to able to do something, right? That's just measuring the processor wake-up time. Of course, any interrupt handling time is actually beyond that in addition to that startup. So at the point the core wakes, it can then handle the interrupt and then schedule nappy and then do the nappy pull work, right?
Okay, Srijit wants to do a follow-up, so I'm just going to bring him on stage here.
Sure.
I'm going to hand him the mic.
Hi, Srijit.
Yeah, hey, actually the hand was raised from like 2 minutes ago, but so then it is what, so maybe I could have phrased the question better. So that 40 microseconds is just C state switch to C0 and then potentially another 10, 20, depending on how badly your interrupts are being held up and everything else, right? So
yeah, and I was simplifying a bit. That's an average, right? So, there's, depending on how the processor's, state and how long it's been in a sleep state and a whole bunch of other things, it can take, all over the place. It's a histogram, right? So the histogram top point would be the 40 microseconds.
So I'll jump to the last comment. It was more a comment than a question. I'm wondering if, there may be an interesting trick here to pull, which is to look at the nappy pole length, right? Which is how much work is waiting. And if you see that you just transitioned out of C6 or out of C5, that may be a good enough hint to say, hey, you know what, this is going to happen again.
Right. Yeah.
Work is building up.
Yeah. In fact, I've actually been thinking about that already. There are some power management APIs for the system that are in the kernel already. We could tell the kernel to keep a recently running nappy thread awake, like for, we're in a low latency exit state for a while after a nappy ran, just like opportunistically burning some power in case we got woke again.
Yep.
I wanted to try that or have somebody else try it and see what happened. It's a little bit tricky in that a lot of the granularity on the APIs in the kernel is wrong level, like it's whole system wide or whole package wide, which is kind of sucky because you have power management basically possible per core, which you can do from user space, but it's like really hard to do from kernel calls, which is weird, right?
Though you then have the tricky part, especially on Intel CPUs, because your package controls your root port, which means and your root complex, which means you have to be careful to make sure that you didn't give your thread power, but not your root port.
Right,
so
right.
package power has to be maintained. C states can be better. Anyway, I think you get the point. Sounds great. Sounds like you're looking at it. I'm done.
Yeah, we want to follow up on that for sure.
Okay, so we have plenty of time. I'm just going to put a comment for a second there from Joel, and then I'll go to the next question.
Okay.
Okay. Next question is from Salil.
PowerMAN seems super. Yeah, it's a good joke. Yeah. Thanks.
All right, there's the question from Salil. And again, anybody wanting to jump on stage, think maybe it should be related to the question. Then I'll, or otherwise I'll go by the queue right now is the Q&A questions. Okay, go ahead.
So yeah, we skipped a bunch of questions as they came in there, Jamal. I don't, but maybe top. That one got voted to the top or something. So anyways.
I don't know. Yeah, I'm going to go through all of them. Yeah.
Okay. Yeah, we'll get through all of them, everyone. The EEE, energy efficient Ethernet, is really slow, and it's really targeted at 1 gig and maybe, you know, if you're feeling opportunistic, 2.5 gig connections. The exit latencies for EEE are really, really, really slow. We've never enabled it on any of our server parts, and I don't think anyone has. It's, you know, really focused at client or automotive usages or industrial or something that can handle these ultra high, you know, restart times basically. And the other thing is that as it turns out, for instance, in a server, the network card and the link is not a big power user compared to the CPUs, right, or even the RAM. So saving, you know, a watt, or maybe if you had fiber, like a few watts of power on playing with the link power is kind of a loss. It's just like trying to play with a PCIe link power management, which is another level of power management that's somewhere between the network stack and the edge of the system. The playing with those power things doesn't save you enough to make it worthwhile in the grand scheme, in my opinion, right? You've got a system that has like a 400 watt power envelope, and you're playing around saving, you know, a half a watt, like, and causing a lot of side effects from it, like, you know, huge latencies, really unpredictable jitter, a whole bunch of things like that, and also, you know, conceivably lots of extra bugs with where your link doesn't come back, or you lose your device, or right. It's not, I don't think it's really worth it in the end, especially for server speed, data center speed links.
Okay, raise your hand, Salil, if you want to go on stage. I'm going to post your next question here.
Is it, yeah, predicting an idle state. Again, is network traffic predictable at all? I would say probably not, unless you have some kind of a load balancer orchestrator on your data center that's able to you know, like give you a heads up. I'm going to send some packets your way soon. Nothing, you know, there isn't really anything that I can think of that would allow you to predict the network state. The idle states for the CPUs are very predictable. In fact, they're managed by the software. Ideally in the kernel. So the problem is that an idle system is idle, right? And if you have power management enabled, it's going to try and turn on power savings. We don't like the CPUs to try and manage themselves. It causes a lot of problems for the kernel. So if the kernel can be aware of the power management schemes of the CPU, which like the Intel idle driver usually is, of all the Intel CPUs. So and then there's a comment here about latency to bring down and bring up the PHY again. Maybe that's in reference to the EEE question, energy efficient Ethernet. So Leo, if you wanted to talk afterwards about this, I'd be glad to. But yeah, there's not much more I can say about that that I haven't already said, I think.
Okay, I'm just going to hand the mic to him. Just want to say as well, we have a puff table at the lounge after this. Maybe we can meet up this break after this.
Absolutely.
Questions.
Yeah, we'll be there afterwards.
Yeah, sure. Thanks a lot, Jesse. Yeah, I got the answer, I think.
Awesome. Thank you.
Thank you so
appreciate
much.
the questions.
Yes, thanks.
All right. Next question is by, well, yeah.
This guy Jamal. Always asking.
Who is this?
Yeah. So is it practical to consider disabling C and P states when you have high-speed interfaces? So I don't think it's a great thing. And in fact, we've been migrating our internal benchmarking methodology to leave some level of C states enabled, because with them enabled, you get turbo. So oftentimes, actually turning power management on helps benchmarks, especially any single-threaded benchmarks, right? Where you can really pump up one CPU and it can use more power envelope to run fast. So yeah, turbo helps a lot. And it can get things done a lot quicker. So you can have like, almost twice as much processing bandwidth out of a single core when it's in turbo, or at least another good 30% almost always, right? So I don't think it's super recommended. And that's the thing that I was saying at the beginning of the presentation, right? Recommending to a customer that they just sit there and allow their system to idle away at 400 watts or 275 watts or whatever, some C0 state idle is just in case packets arrive is kind of a lame setup, but you're burning a lot of extra power. So unless you have money to throw away, it's not a great thing. If you're a financial industry, they could run all their machines in their data center and cool them as much as they need to keep them idling in C0. But I think for a lot of data centers, they're much more power sensitive and heat sensitive. So power management is a big deal.
Yeah, so the only reason you turn them off in a benchmark, like we did in our testing, for example, of the ACOs, is your variability, right? You really don't want
predictability. Yep.
The next one just slightly different, then you start scratching your head. Maybe I did something wrong, so we just turn them off. But perhaps the idea of keeping them off longer when you the idea you mentioned earlier on, where you as soon as the nappy poll, for example, is over, you still stay around for a bit, some heuristic like that, where if you get to the point where you have to disable C state, for example, keep it for a bit longer. And there's ways to predict what kind of traffics you have, because you can sample the arrival rate and figure out, there's a pattern. You can observe a pattern over a long period of time and be able to predict how much, whether there's a packet showing up in the next 5 seconds.
Sounds like a good opportunity for machine learning.
It would be excellent. And now you can put that term machine learning on there. Okay.
Yeah, exactly. Now we can tag this AI hashtag. Let's go.
That's right. Okay, next question is from Alex. If you want to come on stage, Alex, let me know. I'll put you up.
Yeah, Alex, you have a good point. Are we introducing reordering issues? Well, I mean, if it was significant, it would add to a lot of retransmits. The stack is pretty resilient to drops and handling retransmits as it is already. And you could see from those, from our charts, that we were dropping a lot of packets and getting a lot of retransmits as the thread counts increased. PowerMAN helped by helping do workload consolidation there, I think. And, also when you have 128 threads running and you have 112 receive queues, it's very possible that each CPU is waking up, running for like a millisecond, and then going back to sleep, right? Because the depth of the queue was very shallow when it had, even for 128 threads of traffic, right? Each one is only doing a gigabit, right, per second. So they're basically being wasted, right? All that effort of waking the CPU just to handle like 10 packets or 20 packets or 100 packets. So, yeah, I think in this case, the gains far outweigh the negatives for drop packets from reordering. Yes, you run the issue of some reordering as you start dynamically increasing the RSS queues that are available. But on the flip side of that, it's a 50-50 chance when you go to 2 queues and it's a 1 in 4 chance when you go to 4 queues, right? You could actually have one of those queues. You could just end up keep on using the same RSS queue for your flow. So some of the flows might get reordering, but it's a
Okay. Next question is from Shrijit. Okay, Shrijit is allowed only 3 questions. This is his 3rd question. No more after this.
I think we talked about this one when he came on stage, right?
Okay. So I'll skip this one then. Then he's back.
Yeah, I think this one's answered. Yeah, we got it. We got 4 minutes left.
You're allowed one more question. All right. And Christian,
what C-state setup do you set up for your setups? I'm not quite sure that I have the whole question there. We were using, in this experiment, Brett, you want to talk to how you set the C-states up in the script?
Yeah.
So I can clarify. I'm just curious. I've done like switching and stuff before where we turn all of it off so we can get determinism, but that's not always needed, right? So I'm curious. I know that there's some win to go to C1, right? Is that what you're doing, or do you even go further?
Are you asking as far as this experiment or in general?
In general, I mean, are you finding, because you'd said that you're switching your lab over to use C states?
I mean, I think it depends, right? How we set it up for the test that we use. I mean, for latency sensitive tests, I believe that we do disable C states in most cases.
And that's just to get predictability again, like like Jamal had talked about. When you're doing experiments or you're trying to run a test to get a benchmark against, constant apples to apples kind of comparisons, it's really difficult to leave power management enabled to do measurements. Now in production, for sure, I would say, and in our test here, we're trying to actually move this experiment more towards like what it looks like in the real world, because people do want to save power, right? Data centers with 10,000 machines have power caps, right? You can't cool and consume that much juice continuously for all the machines in the data center, right? So,
right. I mean, and well, you mentioned that you have boost, right? So I'm just wondering if there's a setup that I'm not thinking about with some power management where I end up with better power management, but still, as long as it's not a constant flow of packets, better performance.
Oh yes, I mean C1 is for sure in that kind of zone, right? I think even our power management showed it in the charts, right? C1 at all processors idle, the system was about 60 watts. So you get exit latencies of 10 microseconds from the processor. You get much better kind of overall. Your median on exit latency is going to be way down towards that 10, right, or below it, and so your worst case latency for a network interrupt is going to be 10 plus a little.
All right, thanks.
Yeah, so you can save a lot of power by just enabling C1. I mean, you get the majority of the power savings from that, right? So the difference between 60 and 28 is only times 2. The difference between 28 and 280 is 10x, right? So
yeah, and I think C1 even the one we were setting it on is actually 2 microseconds wake up latency. The C1E is actually the 10 for the Intel.
Oh, I had them backwards. Okay, yeah.
So we're even faster and we're saving so much power compared to the C0.
Okay. Yeah, so C1 is that 2 microsecond exit, and C1E is the one I was thinking about. It's the 10.
So I'm going to put Christian off the stage here. We do one more question.
All right. Yeah, we got time for one more.
Okay. And this is from PJ.
Well, I mean, the non-determinism of the run was accounted for that we ran the test 11 times. Right, it took an average. So, yeah, we're at the. I mean, how else do you handle non-determinism, right? You just take a bigger data set.
So 3 was good enough.
3 could be good enough, but when you're running 30-second tests, it's not too bad to run it 11 times.
Yeah, I mean, this is kind of a big shift, right, for benchmarking in general, and I personally would like to see this. I think this is something that we've always struggled with is what is your perfect setup that don't sneeze on it or else, you know, your results go out the window. So having a more realistic view of the world, I think is great, but including, you know, what did it take? And then even maybe having some mentions of like, what does the histogram look like? How much of this data is out of that scope? Because then I see like a trend that could be, I'll run the test 1,000 times or 100,000 times until I see the numbers that I want to see, versus what does this actually really look like?
Well, I mean, running it more times gets you just a really nice average, right? But it's not going to get you the numbers maybe that you wanted to see, because I guess you're talking about discarding outliers, right? Yeah, we didn't do any discards in our data. You're right. It would have been interesting to plot the scatter charts on our data for sure, right? To see the dots all over the place around the average line. And in fact, that's a good point for next time for us.
Yeah, because I think like what you had mentioned in the talk, you're at the mercy of the package state, at the mercy of the PCIe link state, and all of these other things that are all working kind of separately but have the same effect overall. Why would something look so drastically different on one run versus another?
Right.
Not saying that that's a bad thing. I think that's a thing that's been missing in a lot of benchmarking is this is what you'll see when you go try to run this, and this is why. And I think this is like chipping away at that. So yeah, just something to keep in mind that I know that I would love to see on some of these types of talks. So
right.
Yeah, this is good stuff.
Yeah, thanks for the feedback.
I think we're out of time, Jamal. Do you want us to continue here, or?
So we'll invite people to show up at the performance table. Up to 50 people can sit there.
Okay.
Right.
Performance table it is. We'll head over.
Yeah. So this is the best timed session since we started. It's like exactly 46 minutes instead of 1 minute over. Everybody else goes like 5 to 10.
Oh,
so
well.
let's thank Jesse and Brett, and then we'll see you at the lounge. Thank you.
Yeah, thanks for coming, everyone, and thanks for the feedback. Appreciate it. I still want to get my answer to the question about the kernel, Jamal.
Oh, sorry. Do you want to ask that question? That's an important question.
Yeah, I mean, I'll ask the question myself. You know, we were wondering from feedback from the audience whether we should do in-kernel implementation of some kind of scheduler like this. I actually want to use the user space scheduler logic that the Ghost guys did. That was really exciting to me to see that presentation here.
Do you want me to create a poll? It's break time, so we can do the poll right here. There's still unfortunately, a few people left, so we only have
okay.
Okay, so
yeah.
Poll?
Create a poll. Let's do it.
Okay.
Tweak out or something.
All right, here we go.
Someone has a raised hand too. Oh, it's Srijit.
I don't think you can vote twice, guys. I'm sorry. User space. Oh, should we have a third answer? Maybe both.
Well, I mean, that's the way that I would do the initial implementation.
Okay.
All right, polls alive. Kernel or user space, folks.
All right, start voting, please.
The creator did not share the results.
No, you should see the results live as they go on.
It says you marked it to not share the results. It says it right on the screen.
No, I shouldn't be doing that. Okay, there. Can you see it?
You'll have to.
Yeah. Is it not on? I can see it on the stage. Oh, it's not showing the final.
See, this is what we get for trying something new.
No, but this is intriguing. So someone wants to come on stage. Okay, that's Srijit. All right, we'll put Srijit in.
Okay, Srijit. While Jamal's figuring out the stuff, we'll talk with you.
Yeah. So I think there's a third option that's needed, right? So I mean, I think the Ghost stuff is actually very cool. But it assumes a centralized scheduler, which basically has two problems, right? It's effectively a group of processes that will be sort of group scheduled together. So you could say a particular class of apps are going to have something, and then now you're doing a piecewise summation, which is hard for a shared thing like an IRQ, right? Because the reverse maps may not be as clean or as clear as you want it to be.
Can I
So
ask you
yeah.
to submit the verdict on the poll? I think when I close it is when you're going to see it.
Okay.
I can see it. We only have 18 people voting so far.
Well,
Yeah,
you know,
so-
that's more than half, right?
Yeah, it's about half. It's about 50%. Okay, maybe you wait for 10 more seconds and then I'll close it.
So yeah. So Srijit,
20.
you're
Okay.
right. The scheduler is, I mean, where else do I have to go, right? The scheduler today doesn't really get much insight or have any control over like
So-
an application map to a network queue even. I mean, like it doesn't know any of that's happening. We're just doing it all for it underneath. I'd much rather have it be aware at least.
Right. So I'd actually built some prototypes for stuff like this in a past life. But the point I'm making is that's why I think the poll is malformed, because there is a and, because even if you did the user space thing, you do want the kernel hooks to be enhanced to be able to say at least either your IRQ or your queue.
That's probably makes
something.
I think I agree with Srijit actually.
So,
All right, I'm going to close the poll just so it can show so that you see it. All right.
There may be people waiting to talk to us out in the lounge too. So we don't see the results, Jamal, unfortunately.
It's 61 for kernel, 38 for user.
Right.
Okay.
That's what
So
I'm saying. Yeah, 21 to 13 to 8.
13 to 8. Yeah.
Right.
All right.
I don't know why.
Well, good feedback.
All right.
Okay.
Okay.
We should get out of this.
All right. Thanks, guys. So I'm going to end the session here.
All right. Thanks, everyone.
Yeah,
Okay.
thanks a bunch.
All right.